Let's take a look at another example problem from Module 9 for ME12 Dynamics. So in this example problem here, we have a crank that rotates. So this crank AB from here to here is going to rotate at a constant velocity given to us as omega is equal to 150 radians per second. So we can see there is our omega right there, rotating counterclockwise at 150 radians per second. So they ask us to find the velocity of P when theta is equal to 0. So there's our theta term right there, and here's our point P. So they want to know the velocity when our theta is equal to 0. So one thing I like to do with these problems is go through and physically move them. So if this rotates counterclockwise here, then what is going to happen is that moves counterclockwise, and P is going to head over in this direction here. So I just like to understand where everything is going and how the angles are going to change. So as this rotates counterclockwise, our theta angle is going to increase there. So I kind of have a good understanding of how the system moves as a whole if they give us one component that is going to be moving there. So for our plan of attack, what we want to do is we want to define x as a function of theta and then differentiate with respect to time. Recall now our x here is the distance from A to P. You can see that that x distance is going to change as our omega rotates counterclockwise and our P moves in this direction there. Our x will change. So now that I've had an opportunity to read through that problem statement, kind of physically move the components within my model, understand what they're asking us to solve for, and come up with a rough plan of attack, the next thing I want to do is create my setup page. So I have my problem name here, example number 2, my given values. I have my omega is 150 radians per second, my theta is 30 degrees. I redraw out my simplified diagram over here. I have point A connected right here, my point P right over here. I have this distance x, and I have the length of AB and the length of B to P here, all drawn out for me. And I will know that I'm looking for my V sub P, my velocity of P, and my solution, again, is going to be define x as a function of theta to start my solution out. So now that I have all that and I can quickly reference back to my problem setup page and my problem statement page, I can now begin my solution. So again, my plan of attack is to define x as a function of theta here. So first thing I really want to do is go through and do out just a little bit of trig and geometry. So I draw out my diagram kind of as the simplified triangles here. So let's just focus on from A to B here, and I draw a straight line down here. This is perpendicular there. So I have my adjacent, my opposite, and my hypotenuse right there. And if I have my x1 and my point 2 here, my theta here, I can say the cosine of theta is equal to adjacent over hypotenuse, or x1 over 0.2. So that's where I come up with this relationship right here is from that triangle there. And this is cosine of theta is equal to x1 over 0.2. Solve it for my x1. x1 is equal to 0.2 times the cosine of theta. Now similarly, I can do the same thing with sine. Sine is opposite over hypotenuse, so sine of theta is my opposite over my hypotenuse there, or my y over 0.2. Rearrange, solve it for my y. Y is equal to 0.2 times the sine of theta. So now let's go over to the other side of the triangle here. I have my point B, my point P down here. Draw my straight line down here. Now I'm going to call this x2. And now if we look at this, from A to P is my xp. I'm going to call this, and that, or my x as we called it in the previous page. And this is going to be equal to my x1 plus x2. But I just wanted to break these down and have an x1 and x2 for each side of this triangle system here. So if I'm dealing now with this triangle over here, I have my x2, my y right here, and I have my hypotenuse over here, which is the length from B to P of 0.75. I can say, okay, now a squared plus b squared is equal to c squared, so x2 squared plus y squared is equal to 0.75 squared. So I can rearrange this a little bit, solve it for my x2. So x2 squared is equal to 0.75 squared minus y squared. Take the square root of both sides. x2 is equal to square root of 0.7 squared, so 75 squared minus my y squared. Plug in my values now. I already have a value for y that I've solved for right here, so I can take this, plug it in right here for my y term right there. So x2 is equal to square root of 0.75 squared minus 0.2 sine of theta squared. So now we have our x1 and our x2 from our previous slide. And we realize that the total length, our xp that we're going to call here, is a summation adding x1 and x2 together. So xp is our x1 plus our x2, where x1 is 0.2 times the cosine of theta, and our x2 that we just solved for was the square root of 0.075 squared minus 0.2 sine of theta squared. So in order to get our VP, our velocity of our point P, we need to take the derivative of xp. So again, velocity is the first time derivative of position, so we take that first time derivative of our xp, our position term there, and we can get our v sub p. So we can use the chain rule on our x1, which again right here is our x1 right there, and we can say d over dt of 0.2 times the cosine of theta, do out our math, and this is equal to negative 0.2 omega times the cosine of theta. So now we need to do the same thing for x2. We just took the derivative of x1, but now we need to take the first time derivative of x2 to get our velocity. So we take the first time derivative d over dt of our x2, which is 0.75 squared, minus 0.2 times the sine of theta squared, all to the 1/2 is the square root of this. So we can go through here and break it down a little bit. Let's rearrange this a little bit. We take the first derivative, use our chain rule here. We end up with 1/2 0.75 squared minus this whole term here, 0.2 times sine of theta squared, all to the negative 1/2 when we do the first part of this. Then we do the inside of this here, so we go through, and this is negative times a negative 2 times 0.2 times the sine of theta times now what's in this guy here and there times 0.2 times omega times the cosine of theta. So this gets a little ugly. It's relatively straightforward derivatives in calculus, but we can see it's a chain rule, then a chain rule there. We need to really pay attention, keep track of our negatives, do all of our sign convention. So this is where it's a question of, is it okay to still keep going, do this by hand, and really just pay attention, keep track of things, keep your handwriting neat, or do we go to a numeric solver? Do we solve this in MATLAB or some type of other solver, Python, Mathematica, any of those things, where we can actually plug in and get our derivatives that way. So I chose to do it by hand. It's still relatively straightforward enough and simple enough we can do this by hand. So now that we have the derivative of x1 and the derivative of x2, we can then combine these together now in order to get our total velocity of point P there. So we can do that there, add those together. So the derivative of x1 would be their velocity, and our derivative of x2 would be the velocity as well. So we plug those in together, and we end up with this equation down here, where we have negative 0.2 omega times the sine of theta plus 1/2 times now our 0.75 squared minus 0.2 sine of theta squared, all to the 1/2 power times negative 2 times 0.2 times the sine of theta times 0.2 omega cosine theta. So very long involved term there. But we can do some rearranging and simplification in order to make this a little cleaner. So we do that there, and we say, okay, this is all equal to our v sub p, so this is equal to 0.2 omega times the sine of theta, times now negative 1/2 cosine of theta squared, times the sine of 2 theta omega. Realize that this is a double angle identity right there, all divided by the square root of 0.75 squared minus 0.2 times the sine of theta squared. So still, yes, it's rearranged and slightly simplified, and we got it in terms of v sub p, but this is where we really might want to start thinking about a numeric solver rather than doing something like this by hand. So with this here, we do know we have a theta is equal to 30 and omega is equal to 150. So we can go through all of these, plug in where we need to plug in for all those values there for our omegas and our theta terms. And when we do this, we do get a numeric value for v sub p. So v sub p is equal to negative 18.5 feet per second squared. Negative 18.5 feet per second for our units there. And one thing that we do note is the negative sign on this indicates that we're moving to the left.